here's the main theorems that we want to look at it, which is called the mean value theorem. So the mean value theorems basically cut it off one of the conditions from the Rose theorem. A little bit easier to check. So the mean value theorems basically say this: if a function is continuous on the closed interval AB and differentiable on open interval AB, if these two criteria met, then the mean value theorems guarantee that there will be at least one number C, okay, one number C that is in the interval A and B such that, okay, in the interval A and B such that f prime of C that is equal to f of B minus f of A over B minus A. Right? So what does that mean? So look at the picture, it's very clear. It's saying f prime of C, that means what? Is the slope of the tangent line at that point, C. That will be equal to the slope of the secant line, which is like connecting the endpoints. Okay? See that? That's why it's parallel. So that's why I can say that the slopes are equal to each other for two parallel lines. And this C, depending on the functions and the interval that you are talking about, there may be more than one case. So like look at on the second picture. So you can see that what on the second picture, this is what there's two tangent line, right, with the same slope with the slope of the secant line. So I have two different C. Are we all okay with this? So you need to know what the criteria of the mean value theorem so that I can apply this. And the other ones are like a small theorems, right? Little theorems that you already know. So look at this. If f prime of C is equal to 0 for all the x in the interval, that basically means that the function f must be what? A constant functions. We already talked about that way in the beginning. If it is a constant functions, right, it's a horizontal line. So therefore, what? Any x value in this interval A and B, my slope will be always 0. So now this basically helps us to go backwards, right? To go backward. And the other one is also like telling you that if the f prime of x and the g prime of x for all x on an interval are equal, then the original function f minus g is a constant function. Okay. So anyway, what we are interested in is like the first case is how to use this mean value theorem like before, checking their criteria and finding out the value that satisfies the conclusions of mean value theorem. So it's given to you f of x is equal to 1 over x on the enclosed interval of A and B. So you didn't really mention it where my A and B is. So therefore, what I need to do in the first place is, okay, to make sure to narrow it down. I know that the domain of f is what? Everything except x cannot be equal to 0. So, right, to be talking about all the number C that satisfy the conclusions of mean value theorems, we need to make sure that this interval A and B does not include what? 0. So that the function will be what? Continuous on A and B. And the function is differentiable on open interval of A and B. And notice that because this is a rational function, right, within the domain now. So I can basically say this on A and B, not including what? 0, not including 0. That's how I can use the proper notations. Now, I can say that by mean value theorem, since these two criteria is met, it's continuous and differentiable, right? by mean value theorem, there exists a number c such that the slope of the tangent line at that point c is equal to the slope of the secant line on the endpoint. So now we want to find out what are those c values are. So in order to do that, first we find out the first derivative of it. So the first derivative is basically negative x to the negative 2 power, which will give you negative 1 over x squared. And when you evaluate it at c, right, because we don't know what that particular value is, we want to look for it. So when we evaluate at c, that will become negative 1 over c squared. And why do we need this? Okay, why do we need this? Because we can, by mean value theorem, we can say that this value right here is the same thing as what? The slope of the secant line. So now I'm going to be using the conclusions of mean value theorem right here. Okay? So negative 1 over c squared, that is equal to the functions evaluating at b, which is going to be 1 over b, minus the functions evaluating at a, 1 over a, which is the change in y, over change in x, which is b minus a. This is the slope of the secant line that we have. Right? This is the slope of secant line we have. Simplifying it, that will help me to get, right, multiply top and bottom by a minus b. That will give me a minus b over b minus a times ab. Allow me to simplify that, so now I get what? Negative 1 over ab on the right hand side. So cross multiply it, and then get rid of, divided by negative on both sides. I got c squared is equal to ab. So my c is equal to plus or minus ab. So that basically tells me I have what? Two values that satisfy these conclusions of the mean value theorems. And the reason why is because, look, take a look at this. 1 over x, the equation is like this. Right? The graph of this equation is like this, 1 over x. And we will be able to find out, like, here's a, if my interval is on this, I will get one value. And if my interval is on this, I will get another value right here. So I have two of them, right, that I can get, depending on, like, your interval AB is on the left hand side or your interval AB is on the right hand side. Right? Because when the interval AB does not include 0, that could be also only what happened on A. Interval AB is on this side, both of A and B is a negative value, or the interval AB is on the right hand side, which is both of the AB is a right side of on the 0, which is a positive value. So that will help me to get, like, two different C values depending on which interval is. Okay? So this is more of like a generalized answer. Any questions before I move on? Okay. Are we all okay with this? Are we still awake?
Yeah. Yes, sir.
Oh, okay. I worry about more you, because the last time you were yawning all the time, so so I thought you fall asleep already.
Not today.
Oh, not today? Okay.
No.
All right. So here's the next example. Right. This will be a little bit more like, abstract situations that we're going to be looking at it, because it's like all the different, givens, and it never tells you what the actual function is and how do we apply this, like, mean value theorem that we just learned. Okay. So for this case, if you're looking at it, suppose that f of 0 is -3, and the functions f prime of x, so meaning the derivative function's value, is always less than 5 for all the value of x. This is very important, okay? You need to read it very carefully on this kind of situations. All the value of x. And then now the question is, how large can f of 2 possibly be? Right? So you are talking about, looking at this, I have a function value at 0 is -3. And then I want to know that what is my function, how large my function value can be, f of 2. Okay? When it's talking about the derivative of the functions, at any point, the derivative function value is less than or equal to 5. That means my graph cannot be like shoot up like this, way steep. Because if it's very steep, that basically means the slope of the tangent line will be a very large number. So therefore, it limited the slope of the tangent line at any point to be 5. So you cannot be very steep anymore, right? So now with this, questions like how steep my graph can be, that's another way of saying. So looking at this, any questions before I move on? Okay. So looking at this, basically, how do I get the information, right? And the highlighted part, f prime of x is less than or equal to 5. So that means, right, the key part is this, f prime of x is less than or equal to 5 for all x value. That given basically tells me that, right, function is differentiable on any x value for that particular function. So that's satisfy one of the criteria from the mean value theorem. See that? So I put my given is f prime of x is less than or equal to 5 for all x value. So that implies the function f is differentiable everywhere for all the x value. And we know that from the continuity section that we learned, if the function is differentiable everywhere, that basically tells me what? It is continuous everywhere. So that satisfies, so even though we don't know what the actual function is, right, with that one statement that help us to satisfy the criteria of mean value theorem. So now you can see that I put 1 and 2 right there. F is differentiable at, all the x value. And because of that, f is continuous on any point. So by knowing those two, right, now I can say that by mean value theorems, there must exist at least one number c on open interval of 0 to 2. How do I get that 0 and 2? That is coming from here. Remember, we need to relate it, right? This derivative functions, right? The function value of derivatives to the slope of the secant line. So the slope of secant line actually require two order pair. I have one order pair right here, and I need to find out the other order pair, that's what the question is asking you. What is f of 2 values going to be? So I know that the change in x, right, the interval in x coordinates will be what? From 0 to 2. That's how I got my interval right here, 0 to 2. Are we all following so far? See, the problem gives you enough information that you need to be able to look at and then analyze it and put it back into the theorems that we can be using. So now we know that there will be at least one number c on the interval of 0 to 2 such that the derivative of the functions at that particular c, right, the slope of the tangent line, that must be equal to the slope of the secant line. So this is basically the slope of the secant line that we're talking about. See that? F of 2 minus f of 0 over 2 minus 0. Now, the question is asking you how big this f of 2 value can be. That's what we want to look for. So now what we do is what? We use the conditions given to us. Right? From the given, we know that the value of f prime at any x value cannot be what? Greater than 5. So that means since this is equal, right? Since the slope of the tangent line and slope of the secant line is equal to each other, I can say that, right? I can say that the slope of the secant line must be also what? Less than 5. Are we all following so far before I move on?
I don't get why there has to be at least one C on 0 to 2. I get the 2, but I kind of got lost with the 0.
Oh, because the conclusions of this Rolle's theorem is basically talking about what on the equations we are talking about what slope of tangent is equal to slope of secant, right? So how do we find the slope of secant? That will be basically what? The endpoints. F of b minus f of a over what? B minus a. You follow me so far?
Yeah.
So now, what are the endpoints that I can use? Because on the question it's only tell me one order pair is what? F of 0 is equal to 3. So I have one order pair 0, negative 3. And the other order pair is what? The endpoint on the other one is what? F of 2. So that means when x is 2, what is my y value? That's what we are looking for.
Yeah.
So therefore, I already got my interval is what? From 0 to 2.
Oh.
Because this C is always talking about on what? The interval of x. Follow that?
Yeah.
All right. Any questions before I move on? You need to remember that, like, from the picture, let's go back to the picture of the mean value theorem. From the picture, this interval AB, right? A number C is on the interval AB, which is AB is what? On the x-axis. So this is basically talking about what? An x value. Follow? So now, continuing this, right? So since the slope of the tangent line, right, at any point x, for this particular function, it must be less than 5. So that basically from the mean value theorems, right? From the mean value theorems, in that particular interval, the slope of the secant line is equal to the slope of tangent line. So therefore, the slope of the secant line also must be what? Less than 5. So plugging in the value and simplifying it. So this will give me this f of 2 minus, we know that the value of f of 0, which is negative 3, and to get rid of the denominator, I multiply both sides by 2. So that's why it's become less than or equal to 10. And if I want to solve for f of 2, then I subtract 3 to both sides, which gives me what? F of 2 must be less than 7. So that basically helps us to see what is the upper bound of the function value at 2 should be to satisfy all the conditions that's given. Meaning to satisfy this and this, to both of them. Okay? So that the graph will not be too steep, such that the slope of the tangent line in that interval will never go over 5. Are you all following so far?
Yes.
Any questions? Okay. So let's move to the next example, and then the rest of it I'm gonna skip it. Those are not really important. So the next example is like very similar, right? It's given to you right here. The function, derivative function value is between 3 and 5 for all x value. Now we want to show that f of 8 minus f of 2, meaning this is basically talking about change in y values. That must be between 18 and 30. So how do we approach that? Once again, this first statement is given to you. The derivative function value is between 3 and 5 for all x value. That basically indicates that the function is differentiable on all the x value. So therefore, it must be continuous also. So that basically help us to meet the criteria of the mean value theorems. So now the mean value theorems guarantee that there will be at least one number c on 2 to 8, because you can see that this f of 8 minus f of 2, that also right away tells me the interval on x-axis. It must be between 2 and 8. So we are looking for the value of c such that that is in between that's 2 and 8 according to the mean value theorem, such that f prime of c is equal to what? Equal to f of 8 minus f of 2 over 8 minus 2, which is the slope of the tangent line is equal to the slope of the secant lines. Right? So that's only tells you the mean value theorem part, and it doesn't tell us how to get the point that we want to show. So now, how do we incorporate this conclusions of mean value theorem into with something that we already know from the problem? So the problem tells me that the derivative function's value will be always trapped between 3 and 5 for all x value. And from the mean value theorems, we know that, right? We know that between the interval of 2 to 8, the function value and the derivative value, the derivative f prime of c is equal to what? The slope of the secant line. So therefore, I can say that the slope of the secant line is trapped between the value 3 and 5 on the interval of 2 and 8. Okay? Since it is true for all the x values, so it will be also true for what? Between this interval. So from here, if I simplify this, right, in the denominator, that will give me 6. And if I multiply every part by 6, that will give me what? 18 and 30, which is the lower bound and upper bound that we want to see on the change in y. So therefore, we already proved this, or we already showed what the questions want.